All right, recording is rolling. It's Thursday, February 23rd. All right, so a bunch of fun stuff lined up today. Some of you guys picked up quizzes from yesterday, so that's on your desk. All right, so we gotta get started on Unit 4 review, which is energy conservation. I want to hit a few things before that. So there are my other classes, my honors classes and regular conceptual classes, where I hit a bunch of other topics. AP up until the pandemic had a few more topics on the exam that are no longer part of the exam. So I'm like full focus in on the for the review, the stuff that you guys are actually gonna be tested on. But I always feel a little bit bad you're not fully teaching. Well, you guys missing some stuff, right? Missing some labs, missing some content. So I'll put this morning I uploaded some recent presentations for my other classes, thermodynamics, materials engineering. So a few PowerPoints and one lecture. So yeah, if you guys want to see like a crash course on engineering, that was my undergrad major at the end of the day. Do that. There's also we cover waves and electromagnetic spectrum. Now there are a bunch of posters going around. Like right now, I got the thermodynamics and materials posters. It's like Bernoulli principle and a bunch of other stuff going on here. And then all the wave stuff, well, that's been cycle theory. So hopefully you guys have been looking at those, picking up something here or there. But here, at least wanted to do a demo with you guys. I got this glass block here. I keep waiting for like, it'd be good for like 5-minute time. I can show you something like this, but here. So the speed of light is, well, through a vacuum, it's like 3 × 10⁸ meters per second. And that was measured accurately like about 150 years ago. So, right? But it actually slows down inside materials. So it'll slow down inside water, inside glass. Right? And there's this process, like there's a whole explanation again, I kind of skip of why that causes bending, like refraction. So if you stick a straw in water, it looks like it's bent. Like right here, you guys can see the text is like warped as it's going through this glass block. Right? And one thing you do is you can like shine a laser light through and you can watch it and you can measure, right? So you can break out a protractor. Okay, well, that had one at hand here, but here, you guys know what a protractor is, right? So I can shine this laser light through and then it will refract out at different angles. So that's one of the labs you should do with students every year. So anyway, you guys are teaching physics someday. That's a good thing to do. Good lab, got some lasers, got some glass blocks. It's called refraction. It's called Snell's Law, which is one of the posters that has since been moved to the back of the room. We've got Snell's Law back there. Good. If your desk is a little bit sandy, it's because last couple days I had my other classes building a sieve. Here, let me skip to the end of the story. Right, so this here is a show and tell piece from my civil engineering day. Well, when I was a student. So as a student, took a class on concrete. So this is a concrete block. So what they do is, well, in the States, we're still using American imperial unit. So 4 inches diameter, and this was at one point 8 inches tall. Right? We poured these cylinders. Right? So concrete has different size aggregate in it, and water and Portland cement, and you mix that. It goes through a chemical reaction and cures. So whatever water we poured in is like it's gone through a chemical reaction and it's cured and hardened. So left that for about a week, and it came out and put some machine and compressed it. If you know the force per cross-sectional area, you can calculate the stress on it, which is like a pressure. You guys see that poster over there? Concrete can go up to like thousands of pounds per square inch, or you can say like 20, 30 something megapascals. Right? And then what's good, but it's terrible at tension, right? So you pull it out and it'll pop apart, but you can press on it all day. Right? Good enough if you're like building a structure, and then if you can identify any kind of tensile stress, you would not want to just have concrete, maybe steel reinforced, right? Some kind of steel. But one of the things with concrete is if you want to maximize its strength, you ideally want low graded concrete, which means different size aggregate. So like if you have like only large rocks, that could be the strongest part. Like, oh, hey, large rocks, but then all in the middle is just like cement, which is like the weak part. So then you want the medium sized rocks aggregate to fill those spaces, and then like smaller size like sand to fill that, right? All the way down, kind of a fractal type, right? So how can you determine if a soil sample is well graded? It has all different size rocks. Okay, so that's where the sieve comes in. I'll just show you guys this real fast. So again, a project that of course I'm skipping with you guys, but we've been doing the last few years works really good is I got this Griffin treasure. little treasures in the sand. Okay, so how can you separate this out? It's different size treasures, I think, right? You guys see big stuff, small stuff, and then the sand. How do you separate that out? Okay. So this also worked pretty good. Again, I guess if any of you guys are teachers one day, right? So this is a city you can actually build. So we built this last couple of days. I got this box, and then each zip layer. You guys see the top layer. Of course, the professional versions of this they use like wire mesh, right? Okay, but okay, we've got this accordion shape, right? And then like large holes, which will probably like stop the large treasure, but everything else filters through. Okay, and then next layer down, you guys see, oh look, looks like a silk layer with smaller type holes in it, right? Like smaller holes. And then ooh, I'm gonna pop this back in, and it will stop this. So we'll pop those cylinders in place. There we go, like that. Right, and then yeah, so each successive layer will separate on a different aggregate size, right? And the professional ones might have like 2 different layers. And if your soil sample is well graded, then it'll separate out real nice. So you can see that and create some strong concrete. Okay, so obviously I'm skipping a bunch of stuff. I'm skipping like a couple months of stuff, but I've loaded some stuff this morning. So, you know, if you're going to engineering route, maybe take a look at that. Okay. Okay, so AP Classroom, Unit 4, multiple choice part B. I just opened up yesterday. So let's have that due on Monday morning so that you guys come in Monday and we'll go over the answers to that then. I'm going to start over the energy review today. Okay, so this is Unit 4. Okay. Now, I know SAT is next week. Next week on Wednesday is the SAT, which almost everybody here is taking because most guys are juniors. So we're going to have to work around that. That'll be right. So we'll take that today, tomorrow, and next week to review energy. Okay, so let's go to it. Let's get this review, and then we'll hit some AP classroom type questions. Okay. So Unit 4, energy. So energy can take lots of different forms, and in this class we care about some mechanical forms of energy. What was one form that it could take that you guys care about? Yeah. Okay, kinetic energy. That's one form. Okay, and what was the formula for kinetic energy? Yeah, 1/2 mv squared. Okay, so this is energy of motion. If something has a mass and a speed, okay. You guys remember this is here. Energy and work, is that a scalar or a vector quantity? It's scalar, right? Okay. So direction doesn't really matter. No, if you remember back when we were doing this, you can set up and solve lots of problems very quickly with using this method that maybe you could solve other ways that would just take longer. Okay? But maybe sort of one of the disadvantages is that you don't really have direction information, or maybe that's an advantage sometimes, right? Depending on what you're working with and how you use it. Right? So this is, I would say, speed. So 1/2 times mass times the speed squared. What's another form of energy? Yeah. Okay, potential energy. And really, if AP, yeah, right. If AP uses the term potential energy, if there's like a spring involved, like a vertical spring, they might be talking about a mix of both gravitational and spring potential energy, right? So there's gravitational potential energy. Okay, so I'll do capital U for potential energy. I'll throw the subscript G for gravitational potential energy. Oh, what was the formula for that? Yeah, MGH. Okay. Now that's of course assuming that this lowercase g is constant, which I mean if you go from the top of Mount Everest to the bottom of the Marianas Trench, it barely changes, so it's pretty close, right? But if you're sending a rocket to the moon, then if you're sending a rocket to the moon, you actually have to use a more general version of this. Do you guys remember what it is in like sending a rocket to the moon?
Alternative GMM over R.
Yeah, there you go. Negative GMM over R. Okay. And if you have 2 different radial sizes, again, top of Mount Everest to the bottom of Mariana Trench is not proportionally that different from the radius of the Earth. So it just boils down to this. So this is actually a simplification of this. Okay. Now AP almost never asks questions about this. So it's on their equation bank. Right? So you got it right here. It's the one all the way at the bottom. Okay. But you hardly ever see that one. You're almost always using this one here. So delta U sub G is mg delta Y, but delta Y is just height change, right? So that's really what we care about. Okay. And then the other potential energy they might be talking about is spring potential energy. Okay. And if you compress or stretch a spring, and it's an ideal spring, how much energy U sub S is stored in that spring?
Squared.
There you go, 1/2 kx squared. Right? So the force to compress or stretch it is kx, and the energy stored is 1/2 kx squared. Here, we can like put that in a graph. Okay? So we got a spring, right? If you put a force to either stretch or compress it, right, then you say, well, how much does it stretch or compress from its like on stretch length? Okay? What's the force on that? Okay? And what does this graph look like?
Travel.
Okay, well, if you did energy versus x, it would be a parabola, wouldn't it? Yeah, that would be a parabola graph. Now, if I do force versus x, then it should be a linear relationship. We're talking about an ideal spring, which many people always are. Okay, and then what property of what property does graph? What does the slope tell you? What's the slope? Yeah, spring constant, right? So that's Hooke's law, right? F equals kx, right? And then to tie this back to energy, what property this graph tells you something about the energy stored in spring? Yeah, the area under the graph, right? Ooh, does this look like you guys remember work? Is what's the formula for work? Force times distance, right? Now it's a dot product, so you have to have these going in the same direction. Okay. So for example, if I'm lifting something and I'm pulling it up, the direction of the force and the direction of the motion are the same. Okay, so I'm like putting potential energy into it. I'm doing some work lifting it. This is like an energy transfer. That's what work is, right? Energy transfer, force and distance. Okay. Versus if I carry this across the room, am I doing any work on it? No, because I have an upward force, but the direction of the motion is perpendicular to that. So that force and that distance have nothing to do with each other, right? If you sit down and think deeply about this a lot, it does make sense why that would be, but right, okay. So and if I pull this up at some angle, like a 30-degree angle, right, it's only the components that are aligned. Sometimes you can call this the magnitude of the force times the magnitude of displacement times the cosine of the angle between those two, right? Cosine of the angle between those two. Okay, and then it ties back to the spring. You guys see, this is not a constant force, right? It's always a changing force, right? So the more you press or stretch the spring, right, the more force you need, right? Okay, so the more energy it takes, like incrementally, right? So that's why, so this F equals kx, right? And then, yeah, okay. So stretch it out some amount of x, and the energy ends up being 1/2 kx squared, right? So 1/2 times base times height. The base is x, the height is kx, and then the energy stored turns into that. Okay, you guys remember that? Okay. I'm gonna throw one more on here. I'm gonna go rotational kinetic. Okay. So maybe like K sub R, or sometimes they do use capital T, which is used for a bunch of stuff. Okay, so what's the formula for that? It looks like 1/2 mv squared, except you substitute in the equivalent rotational values, which is like 1/2 what I omega squared. Yeah, 1/2 I omega squared. Right? It's not how massive is a point mass. Now you're thinking about like turntables, right? Like this whole disk could have like some rotational inertia. Like it has a mass itself, has some radial size, right? Like the mass is distributed throughout this whole disk, right? Or maybe you're interested in like a point mass, like each one of these coins, right? Be like mr squared for I, right? I is equal to mr squared for this point mass, right? There's R, right? And then omega is like how fast is it rotating? That could be in like radians per second, right? Radians per second. It's turning some angular velocity. Okay? So 1/2 I omega squared. Okay, and then in my honors and conceptual classes recently, we also included thermal energy, which is like MC delta T is like a transfer of thermal energy. Okay? But AP Physics 1, you guys don't care about, you just care about like these right here. Okay. For that. All right, and these go hand in hand. I think when I taught this to you guys, I started with work, force times distance, and if you lift something, some force, some distance, the same things like weight times height, which just is the same as the potential energy you put into it. Right? I mean, these are all connected to each other, right? All right. Let's talk about closed and open systems. So let's start with a closed system. Okay. Now there's sort of like two perspectives on a closed system, two definitions, but they kind of align with each other, right? One is, what would you guys say? What's one perspective on a closed system?
Energy is conserved.
Yeah, energy is conserved, right? There's no energy transfer into or out of the system, okay? Now going hand in hand with that, you could also say there's no net force acting on the system or acting by the system, right? On its surroundings. Okay? And you can set up, here's the framework for this. Sum of energy initial equals sum of energy final, right? Or at point A goes to same as point B, right? So it's good, right? Anytime you see something like changing height, changing speed, oftentimes if there's a spring involved, those are usually flags that it's probably going to fit within this framework, right? Especially, if you're going to identify a closed system, right? Now, if you have an open system, then there usually is some kind of external force. Right? Maybe somebody's pushing on a block and you're looking at the block. They might have like a block falling. Now, if you said like the block earth system, that's back to a closed system. That if you said just the block, right, it's being pulled in free fall, then that would be an open system because now its weight is an external force, right? How about this? How about a rocket going through space and it has its boosters on, like, right, it's accelerating. Could you treat that booster force as an external force? Something like that. And then you might see something like this. The sum of energy initial plus or minus the work done. Okay, some kind of force insistence equals sum of energy final. Right? Oh, another classic example of open system was a car brakes to a stop. Right? The car, here, let's just have a level road. Right? What kind of energy initial? Yeah, kinetic energy. Let's do it. I'm going to draw that one out. And you said it's a pretty straightforward classic example, right? So, yeah, let's say you have horizontal road, so there's no height change, right? Car in motion, the sum V naught. Okay. Yeah, so energy initial would be 1/2 mv squared. Okay. And the car brakes to a stop, so that V final is 0 meters per second. Okay. So what's the final energy? Yeah, zero. What? What's the unit for energy? Joules. 0 joules. Okay. Okay, because let's see, it hasn't gone up any hills, so there's been no energy transfer to potential energy. I mean, like, if your car's rolling up a hill, it's going to slow down a lot faster, right? Because there's energy transfer to potential energy. At least that's from this framework. Okay? I don't see any springs. There's no energy motion anymore. Right? So to complete this equation, I have to say what minus. What's the formula for work? Force times distance, right? In this case, what force are we talking about? Friction. Friction force times stopping distance in this case, right? Whatever the stopping distance is. Oh, it's the stopping distance, right? All right. Here, let's do free body diagram of this vehicle. Okay, free body diagram. Okay, so let's see, just started to hit the brakes right here. Okay. What's one force on this car? Yeah, let's start with its weight, right? Okay. And then because there's a weight and it's on the road, there's also a what force? Yeah, normal force, F sub n. Okay. And finally, which direction do you draw the friction force?
Opposing the motion.
Yeah, there you go. Opposing its motion. Friction force and oppose the motion. Boom. Okay. All right, guys, remember that? All right. Let's do one more classic example, and then we'll kick over to some AP questions. Okay. So one example I like a lot because it involves like all the different types of forces is what if you have a spring, it's compressed, there's a block right here, it's got some mass, and they're gonna shoot this through a vertical loop. Ooh, okay. And one thing you might want to, oops, it's supposed to be like horizontal start now. Okay. One thing you might want to know is like, do I have a stiff enough spring or is it compressed enough to guarantee that the block does make it around the loop? Okay. So I would look right at the top here, and that's kind of like the critical point. Like if it makes it past the top, then it's okay. It's going to make it all the way around. Okay. So let's go from point A to point B. Okay. And that's what you have to do with these energy conservation setups, right? You'll pick 2 points in the system, like, okay, it was here, now it's here. Okay. So let's treat this as a closed system. Closed system. You guys see it's going to have some speed up here, right? B, I'll call it about B top. How about that? Okay. Now, what objects are in the closed system? What's one of them? Okay, the spring. What's another object in the closed system?
Block.
The block? And the earth. Okay. Not all of them. Spring, block, earth. Okay. So they have to say like the spring, block, earth system, or some version of that. The block, spring, earth system. Okay. Okay. So yeah, that's anything that can contain the energy or provide a force of any kind. Okay. So let's set up a conservation of energy for a closed system. Sum of energy at point A equals the sum of energy at point B. Right? Point A, point B. Right? Supposed to be same size block, right? Right. So what kind of energy at point A?
Spring potential.
There you go, spring potential, 1/2 kx squared. Right? I think this is one of the posters I had back. Oh yeah, there's a poster way back there. Right? Okay, so we compressed this some amount x of x. Okay. The more we compressed it, the more force it took. Took slow, right? Press, right? Bunch of energy stored in that spring, and then let it go. Pow! Right now at this point up here, that energy's gone to where and where?
Gravitational potential. Maybe kinetic.
Okay, yeah. Let's go. Actually, that could have been 2. Yeah, I am a lost member or something. So let's say there's no friction. I should have mentioned, because otherwise that could be, if there was friction, we're back to an open system, right? Okay, where there's a force from the track. Right? Yeah, let's go with there had to be this height change, right? H, right? Because it had to go this height change. So some energy was diverted into lifting the block, so mgh, right? So there's some number of joules there, right? And whatever's left over, well, there must be a speed. I mean, because if it peters out right here and loses all its speed, it's going to fall off the track, which is not what we're looking for. Okay. So there better be some 1/2 mv top squared, right? Just like that. Okay. Yeah, and again, if there's no friction, then that's the closed system right there. How about this? How much work did the track do on the block? Zero, right? Because the motion of the block was always perpendicular, always parallel to the go back. Always perpendicular to the force from the track. The force from the track is always a normal force, and the block was always going perpendicular to that, right? So you do the dot product of those, and the track does no work on the block. Right? Now, if you introduce friction, then that's a different story, right? Then the track would do negative work on the block, and that's like so down. You have to subtract force next to fits. Okay, guys with that. Okay. One more thing. If this loop is circular or pretty close to circular, right, I made it more like a roller coaster track where that centrifugal force builds up slowly, right? But let's say it's like a circular track. Okay? Then what is the height of the circle in terms of its radius? 2r, right? So you might do mg times 2r here, right? That could be 2r, right? So sometimes you see that. Okay. Right, you see that? Oh, and then I like to also mention something about rotational kinetic energy. What if I didn't have a block? What if I had like a marble, right? Do you think that marble would also be spinning? So I'd have to add in a term plus 1/2 I omega squared, right? But if some of you guys go to university, take physics there, they might include that also. They might say if that's a marble or do plus 1/2 I omega squared, right? And that'd be like okay. All right. So you guys got a blank board page in front of you? Okay, so write your name on that. And what we're going to do is skip over, and I got some extra energy questions lined up on AP Classroom.